In fact, I actually make the mistake, right? So at plus 1, right? So given at equal to I, at plus 1 cannot be I here, right? So I make a mistake, right? So because we are really just that we have to, right? So going back to this example, right? So when we move from at to at plus 1, we have to flip some of the variables. If we don't flip it, we are going to basically say that like it's already a feasible solution, right? When we flip the variable, like either we hit some regions where we hit the right variables to correct them, or sometimes there's a chance that we hit the wrong region, right? So in this case, we the number of disagreements also is incremented by 1, right? But it's never possible that like after I flipped one variable, the number of disagreements it remains not changed, right? So this also means that probability of xt plus 1 equal to I plus 1 condition on xt equal to I is less than a half, right? So what are we doing here, right? So let's say like we are constructing a Markov chain, right? So the Markov chain is it's really just the state of the Markov chain is the integers, right? 5 all the way down to n, right? Right. So the chain, the I string here is really just the encode, right? The number of disagreements between AT and S, right? So now these two equalities here, right? So if they were true, what they are giving us, they are giving us that like with probability greater than half, it's moving to the right. With probability less than half, it's moving to the right, right? So that's the same for all the states, right? So for all the states that are going towards this direction, right? It's less than half, right? So this is greater than half, right? If so, let's see. Let me just make sure that I'm drawing things carefully, right? So, right. Right, so let me even not look into that, right? So if I look at only the transitions moving from left to right, right? So that the backward transitions, everything is less than half, right? Right. And then if I look at the forward, like the going back, like the forward transition, forward in the sense that we are moving back to the zero state, right? Everything here is greater than half. So on and so forth, right? So the zero state here is our favorite state, because when we hit the zero state, that basically means that the AT is consistent with S, which because S is a feasible solution, our AT is also a feasible solution, right? So the question here is that now we stand in here, right? So we start with an arbitrary assignment, right? So we randomly walk along this random walks, Markov chains, right? So we just keep walking, right? So when we hit zero state, then at the end, then we are not going to move anymore, right? So and then there's only finite number of states, right? So you just keep walking according to this Markov chain. At some point, you will get lucky, and then you will be able to hit this Markov chain, right? We are going to be able to hit this zero state. The question is really just how much time is needed? How much time is needed in order to hit this state, right? Right. So that's actually the next step, right? So that's conditioned on we know that the probability, this two probability inequality holds, right? At least the half of the probability is moving forward. Forward means that you move to the state we love, right? And most of half of the probability is moving backward, right? Why is that, right? So why this is true, right? So let's just rewrite this down, right? So why probability of xt plus 1 equal to I minus 1 condition on xt equal to I is greater than half, right? So really you should look at S and AI, right? So there are two assignments, right? So and then we also look at a lot of courses, okay, C1, C2, C4, C3, C4, all the way down to Cn, right? So S by definition is a feasible assignment, right? So that basically means that all the clauses set to be 1, right? And AI, right, or let's call AT, by the definition that at the T step is still not satisfied, right? So there will be some clause that's set to be 0, right? So there will be other clauses that may be set to be 1, and some could be, it could also be 0, but there, right? So, but the point is that the number of zeros, right, is the number of clauses that says to be 0 is non-empty, right? We will find some I such that ci sets to 0 if we use the AT as our assignment, right? Right. So now here, right? So let's say that like ci, like let's call this a ci, right? For ci, if I look at the assignment S, it sets to 1. If you look at the assignment AT, it sets to 0, right? That basically means that if ci consists of two variables, xi1, xi2, right? So if ci is really sort of in this form, consists of two variables, that basically means that one of these two variables, if I look at the xi1 and xi2, and look at this two variable, and I look at how S is making decision on these two variables and AT is making decisions on these variables, right? Let's say, let me just say that if for X, S, like this two variable, one says to be 1, the other one says to be 0, right? So let's say just hypothetically it's set in this way, right? So now, what this is, right? So this is what we can see. If under AT, right? So we also have, that's completely consistent, like AT's assignment on xi1, xi2 that appears in ci. If this is consistent, it's under AT, like these two AT's assignment for these two variables are completely consistent with S, right? So it is consistent with S, right? That actually implies ci will set to be 1, right? So that really implies our because we set this the variables that appears that in ci exactly the same as S, right? So if S under S assignment ci has to be 1, here it also has to set to be 1, right? So this is impossible to happen. Right. So that basically means that at least one of xi1 or xi2 in AT is different from the assignment in S, right? So maybe xi1 is different, right? And xi2 is not the different, or maybe xi2 is different, xi1 is not different, right? So let's say that, so let's notational wise, let's just call this one xi1 condition on S doesn't equal to xi2 condition on AT, or right, xi2 condition on S doesn't equal to xi2 condition on AT, right? So condition on basically means that what's the value of xi1 under the assignments of S, and then I1 doesn't equal to I1, sorry, there's some notation issue here, there's some typo here, right? So one of these two events are going to happen, right? So xi1 is not the same in S, is not the same as xi1 in AT, or xi2 in S is not the same as si2 in AT, right? So our algorithm will pick up ci, right? So it will like an arbitrary ci. You will pick up an arbitrary clause that's set to be 0, right? And let's say that this is ci, right? So our algorithm will pick up ci, and then you will randomly choose one of the xi1 and xi2, right? So, right, our algorithm will randomly flip one of xi1 or xi2, right? So imagine that, like, you consider an example in which for the xi1, S's assignment is different from A's assignment, right? So this is the inconsistent variable, and then this is the consistent one, right? Then in this case, with half of the probability, we switch the xi1 from we switch our assignments of xi1 from 0 to 1. And with half of the probability, we switch this xi2 from 0 to 1. Right? What does that mean? That really just means that what's the implication here? The implication here is that with at least 50% of the probability, we will flip a variable such that x and at are not consistent on. Right, so that's the implication, right? So just because that our CI sets to 0, that means that one of these two variables in SAT has to be fixed, because otherwise, if they are all consistent with S, the CI would have been true, right? Now, we know that one of these two variables needs to be fixed there, and our strategy is really just to randomly fix one. Then with half of the probability, we hit the right, at least half of the probability, we hit the right one. And most half of the probability, we hit the wrong one. Why it's not exactly half, right? It's also possible that ATs and S are completely inconsistent with these two variables, right? So both variables need to be fixed, right? In this case, like when our random choice will always lead to the fixing at least one variables, right? So in all cases, right, so that basically our conclusion is that the random fix implies that at least, like with probability at least half, one of the inconsistent variable will be fixed. Right. So that translates into the probability statement xt plus 1 equal to I minus 1, condition on xt equal to I is at least a half, right? So let's also pay a bit attention here, right? So sometimes I use xt to represent the random variable that's counting inconsistency. Right, so usually it's a capital font, right? So for this little font, those are really just the variables. Variables appears in the CNF, right? So I think, right? So my handwriting is in general difficult to be recognized, but I think I will try to be careful enough to make sure that the uppercase are not mixed with the lowercase. Right, so that's the reason that let's just write down again what we have, right? So probability of xt plus 1 equal to I minus 1, condition on probability t equal to I is at least a half, and probability of xt minus plus 1 equal to I plus 1, condition on xt equal to I is at least a half, right? So that's the reason that we have a Markov chain that looks like that, right? So the going backward, as I mentioned, it's always greater than half. Right. So and then this is going forward, and going backward is always less than half. Right. So this is actually the terminating state. Once we hit here, we actually find the feasible solution, and then we don't need to run the algorithm again. Right. So our question is that in case we start at some point, let's say this is I, how long does it take to go back to the state 0, right? So what's let's say t would be the random variable that indicates the time it takes to move from I to 0, right? So what's the running time here, right? So you can sort of see that there's a force that's driving us to move towards the left, right? Because there's a higher chance to move towards the left than to moving towards the right. So in general, this is actually because there's only an inequality here, right? So it's actually not very easy to completely characterize the Markov chain, right? So now let's really just use a worse Markov chain. Consider a worse Markov chain, right? Worse in the sense that let's say that the transition probability is always half. It's the half everywhere. So let's compare these two Markov chains, right? Let's imagine that we both start at a particular position, right? So let's both start with this position, and we want to really just understand like both of our goal is to be able to hit the leftmost point. Like let's consider this game, right? So we want to be able to hit this good state, right? The leftmost state is the good state. We want to be able to hit that, right? And we want to understand both the time it takes for the first train to hit that, and then the time it takes, let's say t prime. It's really just a random variable to for represent the time it takes from this state from moving from the I to 0, right? So but it's under a different train. The difference here is that we assign the probability here to be exactly half, whereas we only know that the probability in the transition matrix we care about it's moving forward, at least a half, moving backward, and most a half, right? So like these are really just the only difference, right? So these are the only difference from inequality to equalities, right? So now you can sort of see that like because there's a higher chance, like if I compare like this moving back over here, right, moving back over here versus moving back over here, right? So originally the process, like for the process we are really interested in, it's the moving back probabilities is at least a half. Here we actually reduce the moving back probability. It makes it a little bit harder to move back, right? So it's a bit harder to move back, right? So when it's a bit harder to move back, right, in general you can sort of know that, right? So every single step for the second train here, it's really just a bit harder to move to the right, right? So it's not surprising that we can actually show that the t is actually can be like it's really strictly smaller than t prime, right? So what do I mean by smaller? Because both of them are random variables, right? So in order to show that like we will need to develop more rigorous argument called the coupling. And it's you really just intuitively correct, and then in order to make this whole argument rigorous, it's also not difficult, but we are going to just skip that, right? So it's really just the intuition is here that we need to analyze the Markov chain, but for the chain we want to analyze, the probability is only bounded, right? So now instead we design a chain so that we know for sure that moving from a specific state back to the good state, it's going to take more time, right? Because we make the moving back forward the probability to be smaller, exactly half, right? Now we can sort of like it's okay. We should be able to argue that E of t is less than E of t prime, and then now we focus on understand E of t prime, right? So E of t prime is really just that you have a Markov chain, right? So it's really just a symmetric Markov chain here, right? So every state which happens with 0.5 probability, right? So the only difference is state 0 and state n, right? So in state 0, it's goes back to 0 itself is probability 1, and in state n, that's you disagree with everything, right? So whatever you do, you will always be able to move back, right? So you will not just stay in your place. Right. So we sort of want to understand that, like say in the worst case we start at the situation where most if not all the variables are set in the wrong way. Then how long does it take to work from right to left, right? How long does it take? This is the expectation of the t prime. Right. So my definition is a bit inconsistent with the textbook's definition, right? So I just flipped the direction of the Markov chain a little bit, right? So in the textbook, you actually it moves the good state to the right, and let's see whether that's the. So as I said, the textbook flipped the direction of the chains a little bit, right? So the leftmost state in our analysis is the same as the rightmost state, right? So they are analyzing a Markov chain that looks like that, right? So it's again it's everything is symmetric, right? So half of the probability left, half of the probability right, right? So but this is their theory state. It's the good state, right? So the probability that it stays within the good state is 1, right? And then this is actually the worst state, right? So this is, I'm making up this worst state, right? So in this case, that it's not going to stay at the same place, it has to move back, right? Right. So what can I say about that? This kind of things, right? So now we want to be able to define the random variable, right? So define a random variable, right? Zi, right? To be, if we start at a state I, right? So let's call this a state I, right? So it's really just a state 0, 1, 2, right? So it's really just doing relabeling. Its state n is the same as the state 0 we are talking about, right? So but it's the same kind of chain, right? So it's mostly it's symmetric. Really at the two boundaries, it's not, right? So if we start at the state I, how long is it going to take? It's going to take us to move to state n, right? So now, so for instance, we have Zn is that if we start at n, then how long does it take? How long does it take to move from n to n, right? So we start here, like we are already in the good state, right? So we sort of know that Zn equal to 0. And in general, we are interested in the expectation of Zi, right? So this is we want to find, right? And let's also call that the Hi, right? So we sort of just now we sort of see that Hi, like this is the definition Hn equal to n, right? So so basically we can set up a recursive formula, right? So again, let me just draw this again, and then this is I, and then this is n, right? So let's say that we start with time step I, right? So with half of the probability it goes to I plus 1, and half of the probability it goes to I minus 1, right? So if we want to compute the expectation of Zi, right? So with half of the probability it goes to I plus 1, right? So Zi plus 1, and then we also need to our next task is really to move from I plus 1 to n, right? So this is the expected time of the Zi plus 1, right? And this is plus 1, and also plus half of the probability, it goes to Zi minus 1 plus 1, right? So this is the recursive, right? So it's really just that look at my first step. If my first step moves to the I plus 1 state, then what's the amount of expected amount of time to move from I plus 1 to n? That's expectation of Zi plus 1. And because I make the move for one step, right? So that basically means that I have to add 1 here, right? So that's the same for the moving to the right, right? So basically, we do have like when I use the Hi to represent this relationship, we do have the Hi equal to Hi plus 1 divided by 2 plus Hi minus 1 divided by 2 plus 1. Right. Those are really for the i's. Those are really just for most of the i's, right? Not in the boundaries, right? When the I are in the boundaries, things are a little bit more complicated. Hn equal to 1, right? So H1 equal to, right? H0 has to be equal to H1 plus 1, right? So this is H0 because it has to move to the right, right? So this is what we are seeing here. So these are the two boundary points, and then these are in general the recursive we are seeing here. Right. So so basically we sort of have a like, if you look at everything here, right? So this is at least 1 and most n minus 1, right? So we are sort of seeing that this is a system of equations, right? So eventually, right, the number of unknowns is really n plus 1, and the number of equations is also n plus 1, right? So it basically can help us to uniquely determine one solution, right? So So that's like in theory we should be able to find all the HIs, right? So in practice, what we are going to do is that we prove by induction that HI is really just this equal to HI plus 1 plus 2I plus 1. Right, so we will be able to prove by induction by really just using the system of equation here, right? So I'm not going to repeat that, right? So the induction is we're going to miss that, right? So but it's really just the high school machineries, right? So if we are able to prove that, right? So we are really just by knowing Hm, we will be able to know Hm minus 1 equal to Hm plus, right? So right, so 2m minus 1 plus 1, right? So hm minus 2 can also be expressed as hm minus 1 plus 2m minus 2 plus 1, right? So, and so on and so forth. So you can sort of unfold that all the way down to h0, right? So if you do the calculation carefully, it's actually n squared over here, right? So you are actually able to compute all the HIs, right? So the message here is that all the HIs can be computed. Right. So that means that even we establish the worst possible scenario where all our guesses are wrong, the expected amount of time to walk to the correct state is n squared, right? So expected time to walk to the correct state is n squared. Right. So that's sort of like giving you the backbone of the entire randomized algorithm, right? So basically that says that like in expectation you just wait n squared time, eventually you will find a feasible solution if it exists. Right. So let's write down the conclusion we have here, right? So if the feasible assignment exists, then in expectation the running time of our algo is going to be n squared, where n is the number of variables, right? But so this is there's still some discrepancies, right? So just recall what's the objective of our algorithm, right? So if feasible solution exists, right, we want to, with high probability, we want to be able to find the solution in polynomial time, right? And if feasible solution doesn't exist, feasible solution does not exist, then we want to be able to, with high probability, just output no. Right. So this is a bit, right? So this is what we randomize the algorithm needs to do. This is the with high probability. With high probability. Right. We want to be able to find a solution. But here it only gives you the first part. And then it's not even giving you the polynomial time part, right? So it just says that it's in expectation it's polynomial time, but the randomized algorithm needs the worst case polynomial time, right? So worst case means that no matter what, I allow you to have some sort of errors, but you really must have to terminate in polynomial time, right? But here it's that we are running that like for it's really just that in expectation it's polynomial times, right? So there are some discrepancies here, but it turns out it's very easy to fix that if we are able to have the building blocks that helps us to solve that delivers the property that's over here, right? So what we are going to do is to run the algorithm for 2n squared times, right? So now let's say the first time, like by Markov inequality, right? So we have let's say because expectation of t is equal to n squared, right? So probability of t greater than 2 times of expectation of t is smaller than half, right? So this is really just the Markov inequality, right? So that basically means that how does that translate into the property of our algorithm, right? So that basically means that if we run the algorithm for exactly 2 square m times, and if a feasible solution exists, then after 2n squared times, then with probability at least a half, we are going to find the solution. Right? So this is the first step, right? So we are going to exactly run 2n squared time, right? So we are not going to run more than that, right? That sort of fixes the polynomial time, worst the case the problem issue, right? So we give a hard bound on the running time, right? Now, the magic here is that if it doesn't work, the probability here is only half, right? If we cannot find that, what we are going to do is to restart again, right? Start with the same initial assignments, but we just toss a different set of random coins, right? If not found, just repeat this whole algorithm over here, right? So then after now let's try to understand this very basic things, right? So after repeating k times, what can we see, right? If feasible solution exists, right, solution, then each time we success with probability at most a half, right? So that also means that we fail to find anything with probability at most a half, right? So after we run k times, if within any of this time we find a feasible solution, then we find the one we want, right? So only if we fail for this k consecutive times, we sort of still fails, right? So the probability that all k times fails, right? It's because this, when we do the repeat, we repeat the same algorithm. It's a set of fresh random tosses, right? So this the across different trials of the algorithms, this different processes are independent, right? So that's the reason we say that the probability that all k times fails is exactly equal to probability that one fails happens and to the k, right? So it's really just that every time you have at most a half of the probability fails, and then you want all these k repetitions to fail, right? So the fail probability is going to be a half of 1/2 to the k, right? So now if we set, let's say that we set k equal to log 2n, right? So let's say that's k equal to 10 times log 2n. What is the failure probability? Failure probability is 1/2 to the k, right? So which is the 1/2 to the 10 times log 2n, which is actually, if you do that carefully, it's really just the 1/10 to n to the 10, right? So this is very small, right? So basically this is our algorithm, right? So repeat 10 log n times, right? So within the repetition, just run random walk for n square steps, right? So output feasible solution if find one, right? After we repeat that many times, if we still find nothing, really just the output no feasible solution. Right. So now this is our whole algorithm. Now let's try to see whether this algorithm has all the properties we want, right? So the case 1, the input has feasible solution, right? In this case, we sort of show that with probability at most 1 over n to the 10th, we cannot find anything. Right, so just put that this the other way, right? This statement like in an equivalent way, the equivalent way with probability at least 1 over 1 minus 1 over n to the 10th that we find a solution. Right. This is case 1. And case 2, in case the input does not have feasible solution. Right. So of course, like we this whole algorithm will fail, right? So it will always output no solution, right? So that means that actually, in case the input doesn't have feasible solution, we are always correct, right? So that's obvious, right? So whenever we want to output something, we just need to check that whether whatever we are outputting is really a correct and feasible solution, right? In case we know that there's no such a feasible solution, of course we can never find such a feasible solution, right? So in some sense, we are always correct in case 2. But in case 1, we can also guarantee that only with a very small probability we fail, like with a probability that's very close to 1, we are always going to be able to find a feasible solution. Right. So actually, this example is taking me much longer to explain, right? So so basically, I'm not going to be able to cover a large fraction of what I wanted to cover in this lecture. But now let me just make a little bit of comment, right? So magically, we find some solution for 2 set, right? So now we always are greedy. We want to know that whether we are able to use the same algorithm to solve the 3 set, right? Why do we want to do that, right? So as a student or as a researcher, right, you find an algorithm that looks too simple, or sometimes you feel that that you don't really believe that, right? Then you want to try this algorithm on some impossible task and see whether there's any loopholes, or maybe we have been just careless and in doing some of the analysis that's making this 2-set problem such a straightforward problem, right? So we want to see, just do sometimes it's really just we want to do some sanity check to really just see that whether we did anything silly, right? If in case our algorithm still works for 3 sets, that doesn't mean we solve the 3 set. That just means that we make some mistake in the analysis or the algorithm design. That's not going to happen, right? So that's some of the reasons when you have an algorithmic technique, you want to try harder and harder instances and see whether what sort of conclusion you get. Just make sure that you don't get strange things to just serve as a sanity check, right? The second reason is that I personally very like this idea because it's really more or less helps you to visualize where is the computational barrier when we run a very natural algorithm, right? So when you say an algorithm, a problem is NP hard, and then you sort of like build up a Turing machine and then use the set, right? So you look at Steve Cook's like the NP complete the proof for the set problem, right? So you emulate the Turing machine. That's very counterintuitive, right? But for this algorithm, it's actually giving us some intuition on why it's hard, right? So using it's almost immediately visualize the frictions of this computational barrier, right? So let me just like briefly explain what's the difference, what changes, right? So, and then you can also look at the textbook, right? So now, if we want to do the generalization, the natural general. So what is the 3 set? The 3 set is that it's also again a CNF. Right, so it's really just that each clause consists of 3 variables, right? So could be like that, right? So on and so forth, right? So each clause has exactly 3 variables. Right? So we still have m clauses. Right? So we can still continue to use the trick we said there, right? Say if let's assume there's a feasible solution S, right? So we want to be able to find that, right? So we have an AT that tries to get close to S as much as possible, right? So this is a feasible solution, and then this is the solution we maintain, right? And exactly like what we did in the in the two set problem, right? So we look at this AT, we try to evaluate all the clauses, right? So eventually we will be able, if AT is not feasible, right? If AT is not feasible, right? So we will be able to find the CI, right? Let's say that it has three clauses, xi1, or xi2, or xi3, right? So, right. So sometimes there's a negation, right? So I'm just making this up, right? So then we will find a CI such that sets to be 0, like under the assignment's AT, right? So now we really just randomly fix that. Randomly fix, right? So basically we randomly choose one of them and then flip that. Flipped. Right. Now, so we can use the same argument, right? The same argument is comparing between S and AT are going to continue to be hold, right? So there's at least one disagreement, right, between among the three variables xi1, xi2, and xi3, right? So if I compare these two assignments on these three variables, there's at least one disagreement. If I make a random guess, right? So here's the key difference. If I make a random flipped, right? So then the chance I'm going to guess, if I guess the disagreement point correctly, like if the disagreement were, say for instance, xi1, and I guessed, I just flick a coin, I coincidentally decide to flip xi1, then I'm lucky, right? But because we only know that there's at least one disagreement among three, right? So when I randomly choose one, the chance that we hit the disagreement is going to be at least only a third, right? Just now was a half. Now it becomes a third, right? So that basically means that when you translate into all the notation we were writing, right? So it's basically probability of xt plus 1 equal to I plus 1, condition on xt plus 1, right? So let's say this is I minus 1, right? So, right, I minus 1, condition on xt equal to I is going to be at least a third, right? And probability of xti plus 1 equal to I plus 1, this is getting worse. This gets worse, right? This is more disagreement, right? So this gets better, right? So better, there's less disagreement, right? So condition on xt equal to I is at least at most a third, two-thirds, right? So because they sum to 1. Right. So now when you construct a Markov chain, that's a bit different, right? So this for the three-set Markov chain, I can guarantee that everything here is at least a third. Right. Right. And then everything that goes back, right? So this is the good state. Right. So everything goes back is at most a two-thirds. So on and so forth, right? So now compared to the two set, right? In the two set, we have the same configurations, right? So one-dimensional Markov chains, right? So, but we know that when it goes back, it's with probability at least a half, right? And then goes back with probability at most a half, right? So here, the only key difference is now here is moving from a half to a third, and exactly because of that, then we are going to face a big trouble in the next step, right? So the next step says that, well, let's really consider a conservative train, right? So let's instead of considering at least and most, let's just fix everything to be exactly a third, right? And then everything here goes back to be exactly two-thirds, right? So on and so forth, right? So now, this is the state we want. This is maybe some state that we start with, right? The question is that how long does it take to move to the t is the really just the random variable indicating how long does it take to move to the good state. Right? So now if you look at a particular state, you see what's going on here. It's with a third probability, you are making an improvement. With 2/3 probability, you are actually pushed towards an even worse solution, right? So you can really just immediately see that, right? So in expectation, right? So the expectation of the xt plus 1, it's if you do the math, like you can actually notice that the expectation of xt plus 1 is greater than expectation of xt, right? Why is that? This is because let's really just keep things in the intuitive level because we have to wrap up, right? So it's because of 1/3 is less than 2/3, right? So you can really just feeling that there's a force that's really pushing you towards the opposite direction of the points you want to see, right? And this force, when it translates into the expected time, you can actually see that the expected time is exponential in n. Right? So you can see that if you just naturally run this Markov chain, it's not only that it's going to be very, it's going to not only no, I shouldn't say not only that, you can see that like compared to the two-set version, all of a sudden it becomes a much more difficult to move from the state where you are to the ideal state, because you see a very, very strong force that are actually pushing you towards the opposite direction, right? So this is actually, right, so what I say that like the first time you sort of start to visualize that where is the computational barrier, right? So this strong force really translates into the running time here. Expected running time is exponential, right? But if you do have an exponential amount of running time, you can really just guess, right? So even guess all possible configurations is going to take you at most 2 to the n, right? So that's basically saying that this algorithm is not going to be much better than the exhaustive search. But the textbook actually did a bit careful analysis saying that like if you tweak the parameters carefully, you are able to come up with another exponential running time algorithm that's faster, or despite that still exponential running time, but that's still much faster than the heuristic, right? The details of tweaking this algorithm, you can look into the textbook. But now, at least today, we managed to describe two things, right? The one algorithm to solve the Markov chain, the two-set problem, and based on Markov chain interpretation, right? You see a lot of Markov chain that's going on here, right? And then we also briefly explained that why this algorithm falls apart when we try to use the same technique to solve the three-set problem. Right? So let's wrap up here, and hopefully I'm going to be able to deliver one more lecture this week. I'm trying. I'm not sure I can promise that. And thank you again for your patience.